Okay, we're going to get started on homework 2, question 1. I apologize for the echoiness of this room, but we have to do what we have to do. So the first question was derive the one-dimensional heat diffusion equation for a material of constant thermal diffusivity. So to get started, I wrote a little diagram here where we have a slab that only gets heated via conduction, and this slab has a length of dx and has a cross-sectional area on the x direction of A, and the temperature field is in units of, has a cross-sectional area on the x direction of A, and the temperature field is in units of x, which is position, and t, which is time. So let's get started on part 1. Okay, so we're going to get started with the first law of thermodynamics. I'm just going to write first law. So we're going to have energy in minus energy out plus anything generated is going to be your E total. Okay, there's going to be your E total. And so that's just how we get started. And for this specific question, we're going to ignore generation because for this example that I have, which is a material of constant thermal diffusivity, there's not going to be any heat generation. So that's going to get us started. Okay, so I wrote a couple things down that we wouldn't be expected to know without a reference. So I wrote our left face and right face heat equations down, which is just derived through Fourier's law. So here we have units of watts per meter Kelvin, and our temperature gradient has units of Kelvin meter per meter. So we would be left with just watts in this case, which is what we want because we're trying to find our net heat. And so what we have is we're going to have our Q in minus our Q out. So that's what we're trying to find here. So when you put these together, you'll end up with this equation, which would be so you'd factor out the K and A, or pull out the constant, I guess. And then we'd be left with our temperature gradient of the left face minus the temperature gradient of the right face. So that's what we'd be left with. And then you can further simplify this too, and you can do Ka to the d squared t over dx. Cool. Okay, so now that we have in and out and we do not have generation, all we need now is our total or stored energy, or heat in this case, which is our energy. So I wrote this down. We have our density, our heat capacity, area or volume, and this is just going to be our rate of change based on time. And then these also units will simplify down to just watts, which will match up here with this watt. So yes, now we just gotta totally simplify everything. So we would have There we go. I just realized we forgot our dx right here when I was looking at some of my notes. So let's move that over. So you have dx here. Okay, now we just got to cancel a few things and clean this equation up. So in this example, our areas and our dx's will cancel. So we would be left with our temperature gradients on this side, our diffusivity. We'd be left with density, heat capacity, and temperature gradient. Okay, so what we're going to do in this case is we're going to divide by our density and heat capacity. So we'd have K rho Cp temperature gradient and then we can also see that a lot of this looks familiar. So this right here is just equal to our alpha from earlier, which is our thermal conductivity. So we can replace that with alpha. So we have our final answer. There we go. And let me just copy this over. Oh, it should still be copied, I think. Maybe not. Okay. Oh my gosh. There we go. So that's how we used Fourier's law to derive the one-dimensional heat diffusion equation for a material of constant thermal diffusivity. And I'm sure you could do this with Colab too, but yeah, that's what we did without using Colab, and then we'll kind of use this example on part 2 I'll use Colab to kind of show this a little bit. So let's get into that. Okay, let's get started on homework 2. So we were asked to simulate the response of a uniform rod through forward finite differencing of the heat diffusion equation and show that there is a critical value of the ratio of thermal diffusivity. Time step to the square spatial discretization beyond which the numerical calculations are unstable. Okay, so let's get started. We'll just title this transport homework 1 P2. Okay, let's add code. Oh, there was already some hiding up there. Okay. Oh my gosh. Okay, so I should have them. Okay, yeah. I had them copied. These are just our imports. NumPy as MP, and our right here is the matplot library pyplot, so we can plot our graphs later. Okay, let's get started. Okay, so the first things we're going to define are our thermal diffusivity, alpha. Oh my gosh. And I just looked up a value for thermal diffusivity that would work in this instance, and this is what came up. So we're just going to use that for this case, and we're going to have nx, this is just going to be our nodes or our steps. So we're going to set that equal to 50, and then we're just going to have our length of our rod. Oh my gosh. And let's just do 0.1 meters, so 100 centimeters. I'm gonna put that there just so I remember it's in meters. Ooh, a little suggestion. No. Okay, let's move on. Okay, so what we're gonna do lastly that I just forgot is our dx is going to be our L divided by our nx, minus 1. So what that's going to do is just take our nodes, which we have 50 different nodes here, and it's going to split them up into even slots, step at a time, like 1 step, 2 step, 3 step. And we'll be using that. Okay, next part. What we've done is we've gotten to the point of where my computer science knowledge stops, so we're just going to go into Canvas and copy and paste this prompt. And we're going to ask Gemini. And then we're going to just add a couple things to the prompt. Make sure that this is one cell of code that follows one function. What I've seen in the past is Gemini likes to overdo a lot of stuff and likes to go all out for sure, and a lot of it I can't even comprehend. So yeah, that's what, hopefully it gives us something, so we're just gonna run that quick. And we'll see if it gives an example that I can give a good explanation with. Hopefully, because I can explain in terms how this happens, but I cannot code every step. So we're just waiting a little bit longer. Hopefully it doesn't totally change what I already have here. At least I hope it doesn't. And this is exactly what I mean when I say Gemini likes to go all. So I'm going to say this is, let me cancel. This is far too much. Please keep it simple and follow one. Let me just do time step through one time step and make one line showing the heat. Keep it very simple and plot it using simple terms. Hopefully this works this time. See, that's still far too, I mean, we can run it and maybe I can explain it, but I can already tell. Maybe it's not too much. Yeah, it's too much. Let me talk to Gemini and I'll see, or maybe ChatGPT, and I can see if I can come back with a better code. Alright, so I talked to ChatGPT and it did a better job than anything that Gemini was giving out. Okay, so here down was coded using ChatGPT. So now I can use Gemini and I'll just say, explain this code. I'll just say explain this code. Because what I can show like this. I'm not too sure about what MP1s is. I know that's array of some kind. And I know that this is, yeah, our time stepping loop as it says. So let's see what it said. Yep. Spatial time steps. Okay, so this is the part I didn't understand too well. Calculates dx, the spatial step, and dt, the time step. Oh, wait, never mind. There we go, time stepping loop, okay. Iterates through each internal point of the rod I from 1 to n x minus 2. The course simulation is the line. This is the explicit finite difference approximation of the 1D heat equation and calculates the new temperature at point I based on its current temperature and the temperatures of its neighbors. Cool. So, and yeah, and then back down here is just all plotting. Let's try running this. Perfect. So what we have here is just our temperature in Kelvin and our placement of x in meters. And then, where's the Fourier's number? Okay, so this is really important because this explains the critical value of the ratio of thermal diffusivity, beyond which the numerical calculations are unstable. So this would be at 0.5, which is like right at the tipping point of unstable. So if we change this to 0.51, you'll start to see, yeah, there we go. We start to see it going unstable, but if we go back to 0.49, you'll see it goes back stable. And then if we even change that to 0.45, you'll see it just remains stable. We can even go really, really low. And yep, everything stays the same. And then we can even go up really high with our Fourier's number, and you'll see, oops, wrong button. You'll see it going really unstable. So yeah, I know that's not my greatest attempt at coding, but this is an SES class, so that answered the question of simulate the response of a uniform rod through forward finite differentiating of the heat diffusion equation and show that there's a critical value of the ratio of the thermal diffusivity and time step to the square of the spatial discretization beyond which the numerical calculations are unstable. So yep, that's how we used AI, mainly ChatGPT and not Gemini, to help us explain transport to terminology using code.